With Gay-Lussac's law, we'll be looking at the effect of temperature and pressure. So if we look at our model again, here I'm holding the volume constant, and if we increase the temperature, let's see what it does to the pressure. The pressure right now is right around 5. If we increase the temperature, the pressure steadily climbs. If you look carefully, you'll be able to see that the molecules are moving a little bit faster than they were. And so they're hitting the sides of the container harder and more frequently. If we allow the system to cool, you'll see the temperature is dropping, the pressure is also dropping. The molecules here are moving slower and slower and slower. We get it down to 0 degrees Kelvin, which is minus 273, we'll see that the molecules will stop. Okay, so let's look at some math. Let's state it in words and with an equation. Pressure and temperature in Kelvin are directly proportional. So if the pressure increases, so does the temperature. We can also write the following equation. The initial pressure, or the beginning pressure, divided by the beginning temperature will be equal to the final pressure, pressure 2, divided by temperature 2. We're assuming here that the volume and number of moles don't change. Let's look at our first problem. So a gas has a pressure, of 2 atmospheres and a temperature of 18 degrees Celsius. And I'm just going to go right ahead and change that into Kelvin so we don't have to worry about forgetting to do that. That's 291 Kelvin. And this is going to be our initial. What is the new pressure? So we don't know what the new pressure is when the temperature is equal to 62 degrees Celsius. And again, we're just going to go ahead and add that 273 to that. And temperature 2 will be equal to 335 Kelvin. Now, our formula for this is going to be P1 T1 is equal to P2 T2. We don't have this is the one we don't have. So we're going to want to isolate P2 by itself. Best way to do that is going to be to pick both sides and multiply them by T2. We can do anything as long as we do it the same both sides. That will mean that T2 here and T2 here will cancel out, disappear, and P2 will be left by itself. So let's rewrite that. P2 is going to be equal to P1 over T1 times T2. And now we can just fill in. P1 is 2 atmospheres. T2 was 335 Kelvin. And T1 is 291 Kelvin. If we do our math on this one, we should get 2.3. The kelvins here are going to cancel out. We've got a Kelvin in the bottom and a Kelvin in the top, so those go away, and we're left with atmospheres. Whoops, get my pen. Okay, so let's analyze this problem. First, they're giving us a pressure, and the pressure is 645 torr. And they're giving us a temperature, and the temperature is 128 degrees Celsius. I'm going to immediately change that into Kelvin, because I know I'm going to need it to be in Kelvin. So these are going to be our initial pressure and our initial temperature. What will the temperature be in Celsius? So our temperature 2 is what we're looking for if the pressure increases. And it's going to increase to 824 torr. Okay, so the formula that we'll be using is that pressure 1 divided by temperature 1, this is the Gay-Lussac's law, pressure 2, temperature 2. The one we don't know is this temperature 2. So the best way to deal with this, we've got an unknown and it's in the denominator. That's going to make it really hard for us to solve for it unless we cross multiply. So if we cross multiply, we'll get pressure 1 times temperature 2 is equal to pressure 2 times temperature 1. So I've just cross multiplied. That's gone over here and that's gone over here. Now we still need to get temperature 2 by itself. We'd like the temperature 2 to be by itself, so if we divide both sides by P1, we'll get the P1s will disappear on this side, and we'll get T2 is equal to P2 T1 over P1. And then we can just substitute in. P2 is 824 torr. T1 is 401 Kelvin. Always change that to Kelvin. That's a common mistake. And we're going to divide by the 645 torr. And we'll see that we have a torr on the top and a torr on the bottom, so we get rid of those. We'll do our math and we'll end up with 512 Kelvin. Now we're going to need to put this into Celsius. That's what the problem asks us to do. So we'll want to subtract 273 to get 239 degrees Celsius.